All right, here's the second part of 1.6. This is section F of pre-cal. We're finishing 1.6, and then we're going to do 1.7. So for Chelsea and Ariella, we discussed how the quiz, take-home quiz, is due tomorrow. Tomorrow we're going to finish 1.7, and then on Wednesday we'll review Thursday's Chapter 1 test. I'll give you guys your practice test tomorrow. All right, an important skill in calculus is to be able to decompose a function to two simpler functions. So to decompose a function, h, find two functions f and g such that h is f of g. Literally, what this means is it's a composite function. F of x, fog, all right, the composite function, this is the same thing as saying f of g of x. Literally, you're plugging in a function in for another function. Okay, so instead of giving you two functions and making you put one inside the other, I'm going to give you a function and see if you can make it, see if you can write it as a composite of two functions. So what we're looking for here, for my example, if h of x is equal to 3x minus 1 squared, literally, can I take something out and replace it with just like an x? That would be great. So I can say, okay, this inside function that I circled, I'm going to have g of x be equal to 3x minus 1. And since I'm trying to write it as f of g of x, I'm trying to write it so the f is on the outside. The outside function is whatever the inside is squared. So I can say f of x is equal to x squared. Now, if I want to do fog, right, as my calc students love to say, fog off, right? Fog and goff. They love saying that to me, and I can't even say anything. Let's check it, and let's see if this actually is f of g of x. If I plug g of x back into my f of x, this is going to be equal to, let's see, we're plugging 3x minus 1 in for x, so 3x minus 1, and then squared. This is exactly what we started with. So we're just trying to decompose, go the opposite direction. Yeah, we're in the opposite direction. Okay, so now that you kind of see it is like a weird way to explain it, I'm not being very clear right now, but hopefully you see. Trying to decompose it, I have one function, I'm trying to make it into two. So let's look. We're trying to write it as f of g of x. So where, do I have a function inside of another? All right, so let me find out what the inside function is. What is g of x going to be in this first example? X plus 2. So if I say it's x plus 2, this leaves me with f of x as equaling what? 1 over x squared. So if I want to check this, what?
You don't need to write the 1 twice.
The 1 twice?
Well, I was thinking they both had to be fractions.
Oh, nah. We're good. Okay, now let's double check. We don't do this every time, but let's double check. So if I would plug this in for my x inside of my f, is this going to be what I ended with? Okay, so 1 over x plus 2 squared. Is this what I started with? It is. So I know that works. So this is what we're trying to find, is the part I circled. But then I was just plugging in to check that we did it correctly. All right, I want you to try out B on your own. Try out B. Okay, so do we see, ideally what we're trying to find is pull a function out that's literally inside of another function. So it's almost like we have a function, we want an inside function. So my inside function, since we're doing fog, right, f of g of x, what I'm trying to find is, okay, I'm literally plugging one function in place of x in my f of x function. Okay, what's our inside function? Can I pull something out? Yeah, 5x plus 2. So if I say g of x is 5x plus 2, that leaves me with f of x being absolute value of x minus 3. This way, if I plug this in place of x right here, I'll get what I started with. Yeah. Sweet. Aha. Okay. Okay. Because f of x is what's left over after you pull out g of x. And just replace it with just an x. C is unnecessarily hard. You should expect questions like A and B. That's something you should be able to do. C, we're going to try it. It's probably going to be confusing. So, is there like a function inside It's hard, right? Because I have an x on top here as well. So if I make g of x equal to x squared, that means f of x, okay, the bottom, it makes it pretty easy. It's just going to be absolute value of x minus, square root of x minus 1.
Wouldn't g of x be x squared minus 1?
Well, if I have it as x squared minus 1, then the top, like, how can I get...
Wouldn't it just be x and then x?
So okay. So if I have g of x be x squared, I'm going to pull out x squared and I'll be left with x. If I pull out x squared here, like, I need to know what should the top be. How do I explain this better? Ideally, when I plug x squared in for my x in my f of x, I should get x over square root of x squared minus 1. So if I plug in an x squared inside my square root, the top just goes to x. Versus if I make g of x equal to square root of x squared minus 1, like, what would f of x here be? I know the bottom would go to 1, but what would the top go to? So I need to have it so when I plug in, I'm looking for the thing, so when I plug in square root of x squared minus 1, it just goes to x. Let's see.
Wouldn't you just do g of x equals x? That way it makes it the square on the bottom.
Okay, so let me answer one question at a time. So first, this is like Jolie's question. This would be really hard to try to figure out what the top would be. You see what I'm talking about? So I want to know, what should this top... It can't just be x, because the top is not square root of x squared minus 1. If I have it as maybe x squared on top, well, then this turns into x squared minus 1. Like, I'm trying to figure out, so when I plug in g of x everywhere where I have an x, like, it should turn back into what my original function was. And the other question someone had, so this is the simplest way. This is the example that's from your book. Did you say you wanted, okay, so next question. Did you say you wanted g of x equal x?
Yeah.
So then your f of x, how is f of x different than our original function? It's not.
So then how come the x is the x squared, right?
Yeah, the x squared,
But
correct.
you don't get x by itself.
You do. Because notice f of x has square root of x on top. And if you plug in x squared into your square root, you're left with x. So let me erase the things that are wrong that we were discussing. Because we're trying to decompose into two functions. Ideally, it simplifies the problem. Like, we don't want to just say, oh, g of x is x, because then f of x is just what our original function was. Like, it doesn't help decompose it and make it any easier. Granted, this didn't make it much easier. It is what it is. So as I said, C is, like, hard. This is not the level, like, I really want you to know. Honestly, you just have to know A and B. Do you understand fog and goff and how to decompose a simpler function like A and B? That's all I really expect of you. Cool. Okay, so that's the end of 1.6. Not too bad. 1, 2, 3, 4, 5, 6, 7, 8, 9 problems. Not too bad. All right, inverse relations and functions. Last new section of the semester. Okay, that's fine. Whatever. If you're not excited, because you know that means review-y time is coming up. And so we have 1 day planned for each 1 day review. Like 3 days of review for the final planned for you. Cool. Yeah. Which is about 1 more than like normal. Normally it's like, oh, 2 days of review for the semester.
Oh, after we finish.
After we do the test. After we finish the test, we're reviewing for the semester. All right, inverse relations and functions. Inverse relations exist if and only if one relation contains b comma a whenever the other contains a comma b. So, couple things from Algebra 2. Inverse functions, literally you take a function and you're going to mirror it, reflect it across not the x-axis or y-axis, but across the line y equals x. So that's what this is showing right here, is the line y equals x. So if I have a function, why did I do it this way? This should be pink. Okay. if I have the function x squared minus 4, I want to mirror the blue across the green. I'm sorry, across the pink. So I'm mirroring x squared across the line, y equals x. So everywhere where it was underneath the line is now going to be above the line. This is a lot of highlighting, I'm sorry. So this is the line we're trying to reflect it across. So if I'm reflecting x squared across the line, it's just going to be y squared. More or less, all of your domain, all of your x values are now your y values. You're switching the x and y values.
Oh, and then you're just graphing that.
And then you're graphing it. So, let me do this. So imagine, can I rotate it? Yeah, okay, let me try this. So, I see the line y equals x. It's what's highlighted in pink. If I take this line, x squared minus 4, and I'm going to rotate it across the line, y equals x, I'm going to reflect it across, it's actually my other function. Because when I rotate it, that didn't accurately reflect it. So imagine, okay, take your head and tilt it at a 45-degree angle. So this pink one is flat, right? Can you see how the blue and the green are just reflected across the line?
Yeah.
Exactly. We're reflecting. Okay.
Well,
Take your head to left. Make it so the pink is flat with your line of sight. Do you see how the blue, if I would flip the blue, it literally is what the green turns into, flipping across the line y equals x. Alright, so if I have my head, so that way this is flat right here. You see how the blue, if I flip it across this axis, it turns into the green? Okay. So that's what an inverse function is. So notice, an inverse function has to be a function. It should pass the vertical line test if we're going to call it an inverse function. That's what we call an inverse relation until we say it passes the horizontal line test. Okay, first things first. Inverse relations exist only if we have a point right here, b comma a, whenever the other function has a comma b. So I made 2 points. So I see a point 0 comma negative 4. That means the other one should have a point negative 4 comma 0, which it does. Then they won't be the inverse relations, yeah. So two relations are inverse only if they literally have the exact same x and y's, except all of the x's of the first are now the new y's of the second. You're flipping the domain and ranges of your functions. If the inverse relation of a function f is also a function, it's called the inverse function, and you denote it as f to the negative 1. So you've seen inverse functions before, right? We've talked about like, oh, if tangent of theta equals 1/2, what is our angle? How would we find it? The inverse. Aha, so you've seen this inverse to the negative 1 before. Chapter 4, we've done it. Okay, so this means if I have a function f of x, the inverse is going to look like this. The inverse is going to be f to the negative 1 of x. And that just talks about how the inverse relation is a function as well. Is my inverse relation up here a function as well? The green one is the inverse. Is that a function? The green one up here. Is this a function?
No.
No, why not?
Doesn't pass the vertical.
Doesn't pass the vertical line test. Perfect. So this is only a relation. Not all functions have inverse functions. Look above at the graph. Y equals x squared minus 4. So this is the one that's in blue. All right, x squared minus 4. And y squared equals x plus 4. So that's the green one. The original graph passes the vertical line test, but the inverse does not. Yikes. All right, horizontal line test. A function f has an inverse function. So we're not talking about relation. Function. Is the inverse relation a function? All right, you'll only have an inverse function if your function passes a horizontal line test. Because if you think about it, if we flip all the x and y's, the horizontal line test for our original function would be the vertical line test for our inverse. That's why it's that way. Okay, so we can go through an example first. Graph each function using a graphing calculator. Apply the horizontal line test to determine whether its function exists. Perfect. Do we know what this looks like with our calculator? Yeah, okay, ready? We'll do it on count 3. 1, 2, 3. Let's try it again. With more gusto, Daniel. 1, 2, 3. Okay, it's a parabola. Does this pass the horizontal line test? No. See? Look at all this knowledge you have in your brain already. Didn't even need your calculator. We'll grab it anyway, just to prove it. Come on. Okay. So we know it's a parabola. We know it's not going to pass the horizontal line test. So in Algebra 2, you learned if a function is 1 to 1, it will have a inverse function. So what that means is every x only has one y. Okay, well that makes it a function. And if every y only has one x, that means we'll have an inverse. Okay, so I'll discuss that a little more in a moment. So I need a graph. I'm trying to graph 4x squared plus 4x plus 1. Alright, sure enough, that does not pass the horizontal line test. Vertical line test, if you want to see if it's a function. Horizontal line test, if you want to see the inverse is a function. Yeah. I'll say it again. If you want to see if a graph is a function, it has to pass a vertical line test. If you want to see if the graph's inverse, right, if the function's inverse is a function as well, you have to pass the horizontal line test.
Oh, so you'd say like inverse.
So I'm gonna say no, doesn't pass vertical line test. I'm sorry, no, doesn't pass horizontal line test. Doesn't pass horizontal line test. This means it's not a one-to-one function. So I'll explain that in a moment. So it looks something like this. So I'm trying to see if passes, does not. It circled 2 points where I was running the horizontal line test. Oops, and it failed. Cool. So not one-to-one. So in Algebra 2 you learned one-to-one. That means every x only has one y value and every y only has one x. It's a one-to-one. But this one's not a one-to-one because notice this y value, whatever this y value is, maybe it's like 2 or whatever, right? Y equals 2. It has 2 distinct x values. So this is not one-to-one. Let's try the next one. Ooh, x to the 5th plus x to the 3rd minus 1. Do we know what this looks like? We know like roughly, right? Since x to the 5th, we know it's gonna look something like this, right? What was I? Something. Oops. No, this is what I was doing with my arms. But the question is it gonna look like that, or am I gonna have like some loop-de-doop-de, like overlap? Right? Am I gonna have like these parts? I don't know. So this is, we know what the end behavior is gonna be. We know it's gonna be facing opposite directions, but is it actually gonna pass the horizontal line test? Let's see. We don't know. Some people say yes, some people say no. Okay, let's see. Do I know the answer? Yes, I do. So if there's a coefficient in front of the numbers versus not, that's the trick. All right, so here we just have x to the 5th plus x to the 3rd. There's no coefficients in front of the x to the 5th and x to the 3rd term. So it is going to pass. I just got to prove it to you. Minus 1. Aha! So it passes. If I do the horizontal line test, right, if I try to draw some horizontal lines, can you guys see this? Yeah, cool. If I try to draw some horizontal lines, I'm only ever touching one point with my horizontal lines. So it looks something like this. Let's see, like that. Yes. Because remember, we're trying to see, does the inverse function exist? Is the inverse relation to this graph an actual function? Well, it will be. Yes. Each y corresponds to only one x. So this means 1 to 1. So I keep talking about 1 to 1. What does it mean? Let's look below. If a function passes the horizontal line test, it's said to be 1-to-1 because no x value is matched with more than one y value, and no y value is matched with more than one x value. So if a function is 1-to-1, this is what I was talking about earlier. You can take the domain of your first function, and now that's your range of the inverse function. Yeah. And then you take all your y's of your original function, and now they're your domain of your inverse. You're switching all the x and y values. Cool. So that's what this is showing you right here. This is straight from the book. All right, so you have the domain and range. You have the domain and range of your original function. And all you do is you flip the x and the y for your inverse function. Now your range is all your x's, your domain of your original. Your domain of your inverse are all the y's of your original. Do we need a moment to think about this? Okay. Cool. So we've talked about like looking at a graph. How can you tell if it's an inverse? Okay. But how do you actually find what is the inverse function? So in example 1, A and B, we said, okay, well, the right one is going to have an inverse function because it's 1-to-1, right? If I draw a horizontal line, it will pass the horizontal line test. Well, what is that actual function? Like, what is it going to be? Well, how do we figure this out? So you determine whether the function has an inverse to see if it passes the horizontal line test. Then, in your equation, flip all your x's and y's. So in the equation, replace f of x with y, and then you change your x and y's. So for example, if I had y equals x plus 1, I would see, right, we know what this looks like. It's a line. Okay, cool. If I wanted to find the inverse function, I replace all the x's and y's, like I flip them. Then solve for y and replace y with f to negative 1 of x in the new equation. So to solve for y, I would say, okay, x minus 1 equals y, and then you ought to replace it. So x minus 1 equals f to negative 1 of x. So that tells me what the inverse would be. All right, state any restrictions on the domain of your inverse. Then show the domain of f is equal to the range of your inverse, and the range of your original function is equal to the domain of your inverse. Okay, so in my little example, what is the domain for my original function right here? What's my domain? All real numbers. My range was all real numbers. Surprisingly, I picked a super easy problem to show you how to find an inverse. So if I'm all real numbers for both of them, the inverse will be all real numbers for both. So now we're going to go through a little harder problem, not just a linear function. Okay, so I'll go through step by step. So determine whether each function has an inverse function. Okay, first we have to see if it has an inverse. If it does, find the inverse function and state any restrictions on the domain. Okay, so first thing we have to do, determine whether it has an inverse to check. Okay, determine it has an inverse. So we got to graph it, see if it passes the horizontal line test. So I have x divided by, and notice I'm using parentheses for 2x minus 1 because I want it to actually be like 2x minus 1 on the bottom, not x over 2x then minus 1, right? Your calculator does order of operations. That's just one thing I'm noticing. Like, it's a common mistake. Just make sure you're using parentheses so that way I'm dividing by 2x minus 1. Okay, is this going to have an inverse function? What will the inverse look like? Do we know?
Wouldn't it be the same thing?
Well, remember, it's going to be reflected across the line y equals x. So it's going to be close to the same thing. But what can x not equal? Do we know? What? X can't equal a half. Okay. So, does it pass the vertical line test? Yeah. It will. Come on. Okay. So we know it's going to pass the vertical line test. So the first step we do, looking at the previous page, first step, determine whether it has an inverse by checking to see if it's 1-to-1 using the horizontal line test. It will be 1-to-1. Right? We saw if I drew a horizontal line, it never touches more than 1 point. Okay. So step 1 done. Passes horizontal line test. Step 2. Step 2 says in the equation for f of x, replace f of x with y, and then you switch your x's and your y's. So I'm listing out like the steps on the left side just so we see where we are. Okay, first step, replace this with y. And then I want to switch out, and everywhere there was a y, put an x. Everywhere there's an x, put a y. So, okay, so I see x equals y over 2y minus 1. But then step 3 says solve for y and then replace it. Okay, so for step 3, we have to solve for y. So this is just algebra. We have to get y by itself. But the issue is there's 2 y's. So I'll multiply both sides by 2y minus 1. That way I get rid of the bottom here. Now I'm going to distribute out my x. Because I want all of my y's on one side, right? Right now I had a fraction with it. I'm trying to isolate them by themselves. So I have 2xy minus x equals y. So I'm going to add x on both sides, subtract y. That way I can really trying to get all of my y terms on the same side. That way I can pull out my y value. So Jolie was right. It's going to be the exact same equation, but we have to state the restrictions on our domain. All right, last thing, to get it by itself, divide both sides by 2x minus 1. So I see y is equal to x over 2x minus 1. And then you have to replace y with f of negative 1 of x. Okay, so that was just following the directions, right? So first, we found, does it pass a horizontal line test? It does. Then we replace f of x with y. Then everywhere where we saw an x, we put a y. Everywhere we saw a y, we put an x, right? That was about right here. Then all of this work going down is just to get y by itself. Just some algebra. And then once you get y by itself, you replace it with f negative 1 of x, right? Showing that this is the inverse function. And then step 4, state the restrictions. So the steps I'm listing on the left, you don't necessarily have to write. Okay, so we have our inverse function. We just have to state the restriction. So this is our inverse, but x cannot equal what number? 1/2. Okay, cool. Perfect. All right, let's try the next one. So notice that the domain for this is all real numbers except for 1/2. The range is all real numbers except approaching 1, horizontal, 1/2. Okay, so you see how x can equal 1/2? That's where my asymptote is. Yeah? X equals when x equals 1/2, that's where my vertical asymptote is. What about my y values? It looks like I have a horizontal asymptote. Do we know what it is? What's our end behavior of this function? Was it approaching as x goes to infinity? What is my y approaching? Well, let's see. Did we do this? I'm sorry. Did we do end behavior where we look at the leading terms? No, we didn't. I'm sorry, I'm getting a little confused between my calc class and this class. So, if I'm looking on the left side and the right side, you look at the terms with the highest exponent, x and 2x. So, what happens if you have x over 2x? X's cancel out. And then as x gets really, really big, this minus 1 doesn't matter. So as x gets really, really big, it seems like I'm approaching 1 over 2, 1/2. And as x gets really, really small, really, really negative, well, this is the same x value, so it cancels out. And the value you're approaching is 1 over 2, which is 1/2 as well. So technically, although we're approaching 1/2 from both sides, we're never actually touching it. So there's technically the domain and range for this one. Like, I want to explicitly write it. Oh my god, I realized that I didn't draw that on the screencast. Whew. Okay, so if I want to find the end behavior as x goes to infinity of x over 2x minus 1, we've done something similar to this. Yeah, where we looked at the graph and it was either approaching positive infinity or negative or 0. Well, this time, if you look at the leading terms, so this is something we'll go over in chapter 2, you're looking at the terms with the highest exponent. So I can rewrite this as x over 2x, well, the x's cancel out and you're left with 1/2. So it seems like if I look at my graph, we're approaching 1/2. Well, a y value of 1/2 as we go to the left end of the graph and the right end of the graph. But approaching is not equaling. We're getting closer and closer, but never touching. So if I wanted my domain of my function, my domain is all numbers except 1/2. So it'd be negative infinity to 1/2, union 1/2 to infinity. But my range, that's weird as well, because my range, literally, we just talked about how the end behavior is approaching 1/2 from both sides, but it's not actually ever equaling. Y is never equaling 1/2. So my range is actually negative infinity, 1/2, union 1/2 to infinity. So the inverse, when you have an inverse function, you always take your range, and now that's your new domain. And then your domain is now your new range. It's just weird because we have the exact same range and domain. For like all 4 intervals are the exact same. It's just weird. Okay, that was the 4th step. State any restrictions on the domain of f of -1. Okay, we stated the restriction right there. Then show the domain of f is equal to the range of the inverse, which we did with those arrows. And the range of your original function is equal to the domain of your inverse. Perfect. You need like a minute to stand up and stretch or something? Are we good? Yeah. Okay. Let's do it. I just think it's going to take an example or two for you to like fully get it. But you've done it before. You've done this before. Yeah. Yeah? Yeah. Yeah. Algebra 2. Yeah. Yeah. Okay, cool. So, let's go through. First, C. Does this pass the horizontal line test? Do we know what this looks like? It's a square root. A square root. Okay. It's all cool. So this -1. So imagine if I just had square root. What's the difference between square root and square root of x minus 1? The -1 moves it to the right by 1. Okay. So this is at 1. And then the 2 makes it, stretches it vertically. Okay. Look at you. You know so much about functions. It's wonderful. This is, okay. That has to do with your quiz. Okay, so this is what it looks like. Do we need to graph it? Sure. What you're going to find is it looks exactly like the way we drew it. Let's see. Oops, nope. Go back, escape. Up. Okay, so I want square root 2 times square root of x minus 1. Okay, that's exactly what we drew. Good job. Look, that's what we drew. Amazing. Issue. What about the x values less than 1?
There aren't any.
There's not any. So what does that tell us about the range of the inverse? There's no y values for our inverse less than 1. Oh, because remember the domain and range flip. So let's explicitly say this. Okay, so for my original function, my domain is going to be 1 to infinity. What is my range of my original function? Where's my range? The y value, the range. What's my y? My interval for my range?
0 to infinity.
0 to infinity. Wonderful. So we know the range is our x values. The domain, did I just say it wrong? The domain is our x values, the range is our y. Okay, so first step, passes horizontal line test, check. Let's go on to the next step. So, next step, replace f of x with y, and so we'll have y equals 2 times square root of x minus 1. And then we're going to rewrite, flipping the x and the y's. Everywhere there was a y, put an x. Everywhere there was an x, put a y. And then, now the rest of the problem, the hardest part, getting y by itself. Getting y by itself. So divide both sides by 2. Actually, I'll give you guys like 10 seconds or so, see if you can get y by itself before we do it together. Okay, that's a good little exercise to see how your algebra is. So, we get y by itself, but secretly this isn't our actual function y, this is solving for inverse, so, step 3 is replace the y with your f of negative 1 of x, right, your inverse function. Okay, so we found it. What's the restrictions on our domain? Huh? So for my inverse function, the range is what my old domain was. So my range is going to be from 1 to infinity. And for my inverse function, the old range of my original function is now my new domain. So my domain is, my restriction is only from 0 to infinity. That's the only place it's going to be defined. So if I wanted to, let me graph this on the same graph. Let me graph the inverse on the same graph. Okay, cool, you can still see what I wrote. So, I'm going to graph my inverse function. So x squared, hold on, actually I want to restrict the domain. So I need my template. Okay, so I want it to be x squared plus 1. Oops, I don't want that plus 1 in there. Plus 1, but only if x is greater than or equal to 0. Oops. What? Syntax, man, okay. I'll graph this other one. 2 times... Oh, I want it to be a function, never mind. Cool. Okay. So, oops, this is not easy to see. I'm going to graph a third function here, y equals x. So, do you see this black line? Oops, I forgot the over 4. Dang it. 1/4. There. Do you see this black line? And the blue and the red? If you take the blue and reflect it across the black one, it turns into the red. Change my window to quadrant 1. Okay, that's a little easier to see. So, the black line is y equals x. This is the line you reflect across when you're finding an inverse function. The blue line is our original function. So, if you tilt your head so that way the black one is literally your horizontal, you can see the blue, it flipped across, the blue and the red are mirror images of each other. So that's how we know, oh, they're inverses. Awesome. So notice that the domain of your blue, right, the domain, we go from 1 to infinity. That's our range of our y, our inverse. The range goes from 1 to infinity for my red. The y values, the range for my blue goes from 0 to infinity. Well, the x values of my inverse, right, the domain range switch, the x values of my inverse go from 0 to infinity. That's what I'm trying to show you right here, is that they literally switch. The domain of my original function is now my range of my second one. Okay. So, show they are inverses of each other. Do I want to get to this one? Oh, we still have like 15 minutes. Let's do it. It's great. Yeah. Do we have questions about this so far? Perfect. Compositions of inverse functions. So 1.6 was compositions of function. Literally, you have a function inside another one. All right, compositions of inverse functions. Two functions, f and g, are inverses only if fog and goff are equal to 1. Okay, so what this means is if you take f of g of x, right, and f of x and g of x are inverses of each other, when you put the one function inside its inverse, it should just equal x. And then you have to check the other way. Okay, so you put the first function inside the second one, make sure it's equal to x. Then you put your second inside the first and make sure when you simplify the algebra it's equal to x. And that's how you tell they are inverses of each other. Okay, so let's try it out. Show algebraically f and g are inverses of each other. Whew. So all we're doing is verifying. Let's do fog first. So, oh my gosh. F of g of x. What I'm doing, f of g of x, I'm plugging in my function g of x everywhere there was an x. So I'm plugging this in place everywhere there is an x. So this is equal to square root of x squared minus 10x plus 33 minus 8 all plus 5. So once you plug it in, it's just some algebra. X squared minus 10x plus 25 plus 5. Notice the plus 5 is outside. But wait, the inside, if I wanted to factor the inside, is a perfect square trinomial, meaning perfect square trinomials have two of the same binomial factors. So if you have the middle and square it, you should get c. So half of b is equal to, take half of b, square it's equal to c. Do you know what I'm talking about? B and c? Ax squared plus bx plus c, the standard quadratic form. Okay, so what I can do is write the inside equal to x minus 5 times x minus 5. Or you could say what adds to negative 10 multiplies to 25. I didn't necessarily have to show you that step. I could have just went straight to this one. X minus 5 squared. What happens to the old square root and square? They cancel. Yes. Then I'm just left with x minus 5 plus 5. So that's just equal to x. Perfect. So we're proving they're inverses of each other. This is what should happen if you plug a function into its inverse. You should just get x at the end. Okay, so I want you to try the second half of this problem. Now that we've done the first. Now you gotta do goff. Yep. We did fog, now you do goff. you should get x at the end if these are truly inverse functions. Maybe I should change colors. So now everywhere there's an x, oh my gosh, you have to plug that in. This is definitely the harder one. But it's okay. Parentheses might be your best friend with this one so you don't lose out on anything. Okay, so let me break it down a sec here. So we're plugging in. So we're plugging this in place everywhere where you saw an x. Plug this in place for this x and for this x. Now, the issue is square root of x minus 8 plus 5 squared. You have to FOIL it. It's a binomial. It's a binomial. You have to FOIL it out. So if I would FOIL that out, oops. If I FOIL this guy out, let me show you up here. You have square root of x minus 8 times square root x minus 8, so that's squared, plus 5 times root x minus 8 plus 5 times root x minus 8 plus 25. So I simplified this middle, and that's why I just went straight to 10. If it's a binomial, you have like two terms, adding, subtracting. You have to FOIL it out. You have to FOIL it out. Okay. So let's go through. These square and the square root go away. So I have x minus 8. This 10 times root x minus 8 minus 10 times root minus x minus 8 go away. And I'm left with plus 25 minus 50 plus 33. Okay, so now it's just like math. So let's do this. This is x minus 58 plus 25 plus 33 is 58. Oh, those go away and it's equal to x. Nice. All right, questions on this one? Cool, cool, cool. This is the last page? Sorry, okay. So, to find an inverse algebraically, take x and y, flip them, solve. If you're trying to verify that they are inverse of each other, you literally take Fogger and Goff. You have to verify, you have to plug one in for the other, and you should get x at the end. Okay, so last page of notes. So we'll, it doesn't take long. We'll definitely finish it, and then tomorrow you can have a whole day to work on homework. That works. I'll give you your practice test. That way you have a day to like review whatever finished stuff, and then we'll review on Wednesday. It's great. I wasn't sure how long 1.7 would take, so I was a little worried. But, use the graph of each function to graph its inverse. Okay, so we know that the line y equals x. We're trying to reflect it across this line. All right, so this is y equals x. We're trying to reflect across this line. We also know this passes the horizontal line test, right? This part right here passes horizontal line test. So my inverse relation will be a function. We also know for an inverse function, you take the domain and range of your original and then you flip it. So the domain of my original function now be my range of my inverse. The range of my original is now my domain of the inverse. Okay, let's pick a couple interesting points. This one, maybe this one. Let's take like, I don't know, let's take these 4 points. Those are nice. So for f of x, picked a couple points. I have negative 3 comma 0, negative 2 comma negative 1, 1 comma negative 2, and 6 comma negative 3. Okay, so I picked a couple points. How do I find the points of my inverse function from these points? Do you have any idea? Exactly, flip the x and y. I should have a point at 0 comma negative 3. 0 comma negative 3 at negative 1 comma negative 2. So I'm flipping all of my x's and y's. Negative 1 comma negative 2. Point at 2, let's see, negative 2 comma, negative 2 comma 1. 2 comma 1, and at negative 3 comma 6. Negative 3 comma 6. So if I connect them, hey, right? It kind of looks like I took the black function and flipped it across y equals x. There's my inverse. Nice. If you're done with this one, you can try the second graph. I picked some nice, easy points for my function to find the inverse. Alright, so if I'm comparing my blue and my purple, they're literally just reflections of each other across the line y equals x. Try the last graph. Okay, so I'm gonna draw. I feel like this helps us when we graph. Let's see. Okay. Notice there was an arrow at the bottom, so this graph is going like down forever right here.
Does it touch 0?
It gets very, very close, but doesn't actually touch it. So I have a point at, let's see, right here. Oh my god, this is not even, it's kind of close. Okay, perfect. So I have a point right here, 1 comma 0. Okay, this point right here, I'm just going to have to tell you what it is. This is 2.7 comma 1. This is the graph of ln of x, the natural log of x. That's what this graph is. That's how I know what number it is. Okay, so for my inverse, shoot, did I write inverse up here? Okay, I did. So I flip the x and the y's. So 0 comma 1 and 1 comma 2.7. 0 comma 1 and 1 comma 2.7. And then, since I'm approaching, well, let me show this. Since I'm approaching a y, okay, notice my orange is getting closer and closer to an x value 0, but never touching it. My blue is going to get closer and closer to a y value of 0, but never approach it. Do we know what graph this is in the blue? So you don't have to know this yet, but this is e to the x, is your f of x, and its inverse ln of x. But you don't have to know that. You just have to know how to graph it. Cool. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 problems. It's the last lesson. And then, so tomorrow you can work on homework all day. That way you can get some questions, get through some stuff. Perfect.